All right, so acid-base reactions. So we've got another type of reaction category. We'll call it a category. Our lesson objectives will define an acid and base are. We will list the strong acids and strong bases. Then we will define an acid-base reaction, and we will write balanced chemical equations for acid-base reactions. An acid produces the hydronium ion, H3O+, when combined with water. Why hydronium? In water, the hydrogen ion is reactive, and it will react with the water to form the stable hydronium ion. When we talk about acids in water, this is the form of the H+ that dissociates. This is one of those things where the larger form is implied, but we are sometimes too lazy to write it out all the time. So you will see H+ and you will see H3O+ pretty much interchangeably when you're talking about acid-base reactions. When you see it written as H+, it may be called a proton donor because H+ has one proton and no electrons. It's donating a proton. Strong acids fully dissociate in water. So here we have HCl plus water making the hydronium ion and chlorine ion. Fully dissociates, we give it a one-way arrow. It's only going toward dissociation. Now, what are the strong acids, you may say? This list in red here. So, why are they strong? They have stable anions when they dissociate. So because they're stable once they dissociate, they stay dissociated. If they weren't, they would go back to the undissociated form. So strong acids include HCl, HBr, HI, HNO3, H2SO4, HClO4, and HClO3. Everything else is considered weak. Now, if you're looking carefully, you notice that we have HCl, HBr, HI, and all of those are halogens. So why don't we include HF? Well, it turns out HF is not a stable anion in solution, and so it's a weak acid. Now, finally, why did I make this box in the equation red? When you use litmus paper to determine the pH of your solution, if it's acidic, it will turn red. What about weak acids? Weak acids do not fully dissociate. Their anions are not stable, and so they want to go back to being associated. When we write the equation for a weak acid, we give it a two-way arrow. This indicates that the reaction can go in both directions, and when you have an equation like that, it indicates that we've reached a chemical equilibrium. So what does that mean? It means that you can have the forward reaction and the backward reaction. All of these things exist simultaneously in solution. And when you're at equilibrium, the rate at which things go forward and the rate at which things go back are equal. So the concentration or the amount of each reactant and product is fixed when you're at equilibrium. You need to remember those two things. You'll learn more about chemical equilibrium in Chem 108, but the main points here is that the forward and backward reactions can both happen, and at equilibrium, the forward and backward reactions are at the same rate, which means that the chemical species, like the amount of each chemical species, is fixed at that point in time. Now, I made the weak acid solution or equation pink because on litmus paper you get a more pink color when you text a weak acid instead of that red color. Now, final point. Acids which release one H+ are called monoprotic, and acids which release two are called diprotic. Your sulfuric acid, H2SO4, is included in that list. And those that release three are called triprotic. An example of that is phosphoric acid. So now that we've exhausted ourselves with the acids, let's talk about bases. Bases produce an hydroxide ion in water. Strong bases get a one-way arrow, just like strong acids do, because they fully dissociate. And weak bases get a two-way arrow because they partially dissociate. So all of those species exist simultaneously. Now, this is the simplest definition of a base, and it is the most common example of bases that you will see, just like our acid definition was the most common definition. I made the box of strong bases blue and the equations dark blue and light blue, just like the litmus paper that you see when you test these compounds. You'll note that strong bases are mixed with group 1 and group 2 cations. Every single one. Those cations are stable in water, which is why they make strong bases. They fully dissociate because they're stable when they're in water. The reaction for the weak base that I've given you is an example of one with ammonia. Ammonia creates the ammonium ion and the hydroxide ion by splitting with water. This is true of all bases formed from compounds that contain NH sub X. In organic chemistry, the NH sub X group, we'll write this out here, is called an amine. And it will normally be connected to a bunch of hydrogens, which we call R. Now, this amine group acts as a base in the same way that ammonia does. It accepts an H+. So when it reacts with water, and again, it'll be a two-way arrow because it's automatically weak, we'll get R, meaning hydrogen stuff, NH X plus 1 plus, and an OH minus. And that will happen the same way every time. This will come up in lab at the end of the term, so try to think of a way to save this information for yourself for later. All right, so finally, what is an acid-base reaction? It's the transfer of a hydrogen ion from one chemical species to another, and I have an asterisk here because this is not the only definition of an acid-base reaction. It's the simplest and it's the easiest to see in equation form, but it is not the only one. I don't want you to think when you hit the topic later and we give you more complicated stuff, you lied to me. I didn't lie. I gave you the simplest form. All right, so anyway, let's try to talk this through. Acid-base reactions that don't involve water, excepting a proton, produce water and a salt. Actually, the definition of a salt is the product of an acid-base reaction. Sodium chloride is called salt, and it is the most well-known of all salts. But things like KCl, barium nitrate, sodium phosphate are all considered salts. You need to expand your definition of the word salt for this class. Let's do an example with a strong acid and base reacting together, and we'll write a balanced chemical equation, an ionic equation, and a net ionic equation. Then we'll attempt a weak acid and strong base version, which will be analogous to the strong acid weak base version. And finally, we'll do an example of a weak acid weak base reaction. All right, so let's try our strong. So if we have HCl, nice strong acid, plus NaOH, which is a nice strong base, one-way arrow, we will get water in its liquid form plus a salt. In this case, NaCl, and that'll be dissolved in water. Now, when we write the ionic equation, we're going to fully split up, fully dissociate our ions. So we have an H plus and a Cl minus. Okay, and then we have an Na plus and an OH minus. And we are going to water, which stays the same way. It doesn't dissociate. And our salt, which does dissociate. It's very soluble. Now, if we write our net ionic equation, where we cross off all of our species that are the same on both sides, our spectators, we get a much simplified version of just H plus OH minus going to water. All strong acids, strong base reactions have this balanced net ionic equation. Every single one. Now, when we go to deal with a weak acid and a strong base, we're going to use acetic acid just because it's convenient. We've all heard of it. And that acetate ion is something we need to practice seeing. Remember how I said it could take two different forms? Here we are with the other one in the same presentation. We'll pretend that we can read that as an H. All right, and I'm going to add NaOH, same strong base that I used before. I'm going to start leaving off the AQ just for my own sanity because this is taking me forever. And we make a salt and water, which I am going to label with the L. All right, so when we write our dissociation of this into an ionic equation, we are not going to split up the acetate or the acetic acid. And that is because the majority of acetic acid, when you put it into solution, will be in the associated, not the dissociated form. The base will still fully dissociate because that's a strong base. Sodium acetate is extremely soluble because we've got a group 1 cation and we have an acetate ion. And both of those things cannot help but be soluble no matter what they're combined with. And we got water. All right, so if we cross off our spectators, goodbye, we get a distinctly different equation for a weak acid and a strong base. Than we did for a strong and a strong. And it's because of that partial dissociation that we get this answer. Okay, so let's do one final one, our weak example. So we will do acetic. We'll change colors just to make these visually different. Let's do C2H3O2H again. And this time we're going to add NH3. Do a better plus sign here so this actually makes some sense. Boop. And that will go to NH4 plus and the acetate ion. Now, I could have written that as sodium acetate, but I chose not to, and I'm just giving you the balanced net ionic equation on this one, mainly for my sanity because we don't have enough space, and doing this with a mouse is taxing. All right, now, when you mix an acid and a base together, the reaction is called a neutralization reaction. This is because the solution that results is uncharged. The ions cancel each other out. Okay, so whenever you mix an acid and a base, neutralization. Now, acidic solutions tend to have positive ions, and basic solutions tend to have an abundance of negative ions. That is the only other thing to remember about this. Onward and upwards. Let's give yourselves some practice. I want you to pause here, and I want you to try to write the neutralization reactions for the following. And you may want to go back and look at your strong acid and strong base list. We have barium hydroxide with sulfuric acid, first one. We have nitric acid and CH3NH2, which is a version of that NH stuff that I mentioned earlier. And then we have that CH3NH2 plus CHO2H, which is formic acid. Give it a whirl and see how it goes. Answers on the next slide. Okay, so this first one is strong acid, strong base. So all of them have the same net ionic equation. H plus OH minus makes water. Second one is strong acid, weak base. And so we get H plus our CH3NH2 makes the CH3NH3 plus. So we add an extra hydrogen and it has a positive charge. And finally, we have a weak base and weak acid in this last one, and so we form one positive ion and one negative ion. To summarize, the simplest definition of an acid and base, acid releases an H+, which makes the H3O plus ion, and a base releases OH- when it's dissolved in water. Acid-base reactions transfer H+ ions from one chemical species to another. They are the simplest reactions of this type. You get water and a salt when you do this type of transfer, and the pH goes towards 7 in an acid-base reaction, which is neutral. Strong acids and strong bases fully dissociate, and we have a list of both of them that you will need to know. For the bases, you can just remember that it's anything OH combined with a group 1 or group 2 cation. And for the strong acids, you can remember that the halogens, with the exception of fluorine, and the astatine and oganesson, which are not very common, which is why we don't include them in the list, then nitric acid, sulfuric acid, HClO4, HClO3. It is not that bad, I promise you, but you will have to memorize those. It'll come up a lot. We'll do a lot of problems, but you'll have to memorize those.